Okay.
Right.
Alrighty. Hello, my name is Dylan Mummy. I'm the team.
I'm Preston Whitmire.
And I'm Weiler.
And this is Eagle Eye. Okay, there it goes. Our project advisors are Professor Randai and Clayton Anderson. Our goal this semester is to make a prototype and design a relatively cheap prototype UAV or quadcopter design that we can fly in the atmosphere or out of atmosphere. What we will use is RCS thrusters for an out of atmosphere and a quadcopter and octocopter design blades for thrust in the atmosphere of Mars. Our ultimate goal is for this project to be used by a space organization, either commercial or federal, to assist in spacecraft safety or in spatial body exploration. Current state of design, we're currently in the process of finalizing the overall design concept. We have a 3D model that you guys will see later on, as well as continuing our research on the Mars environment, as well as conditions that we will need for electronics. Mars has a very low temperature, so we are currently researching how to combat against the low temperatures. Our research has shown that helicopter flight is possible on Mars, and that's why we have chosen an octocopter approach for our design. It provides a good thrust to weight ratio, as well as in case one of the motors fail, we can shut off another engine and it will still be able to fly. Starting Eagle Eye, it's kind of my goal to develop something that could help the astronauts both in the space and in an atmosphere. When they're in space, it could be sent out to check for damage on the craft before they re-enter the atmosphere or before they leave. And then when on Mars, it could be used to scout a different path if they found terrain that was blocking them from their current position. Also, it could be used for missions to scout further out from where they are positioned at. I'm going to turn it over to Preston Whitmire.
All right, so here you can see the basic fundamental concepts for our design. The two pictures on the left show the full body and a section view of the main body of the craft. It's an octagon shape, which will house the main electronics like the batteries, the receivers, the transmitters, and all the wiring and circuits and stuff that we need in order to run it. The picture on the bottom left is the outer ring that will connect and secure to the main body, and we'll have the electronic wires running through it to the motors, which will be on the 8 arms that you see around the outside. There will also be a separate ring. This one will be removable, and then you can put the other one on. That one will have shorter arms and will have the RCS thrusters on the end, making it relatively easy to change between the prop motors and the RCS thrusters when you go from in an atmosphere to out of an atmosphere. This is what it would look like with the body and the ring attached. The holes in the body line up with the arms of the ring so that you can run the electronics through it and get to the motors and propellers and RCS thrusters. For cost analysis, for the main part of the body, we're looking to use some sort of carbon fiber. That's what our goal material would be, but we haven't officially decided on what it would be yet. That does run relatively expensive, but it would be best structurally and weight-wise for what we would like to use it for. As far as calculations, the basic helicopter lift equation is shown there. We're going to do kind of a trial and error to find what our best mass to weight and how much thrust we can produce given the motors that we have. We'll use that to determine how much we can actually lift, and that'll determine what motors we'll eventually buy in the end, as well as what material we'll make it out of and how much we'll need.
So obviously, for the fall and spring semester, we're really looking to be able to, since we're an extremely new project, we really don't have anything already set up for us. We're looking to figure out the calculations so we can figure out the mass of the structure, the lift we need, so that ultimately we can create the foam body model by the end of the fall semester, so that we can do some aerodynamic testing and do some battery calculations as well as solar power calculations, because the idea is that we'll use solar power to recharge the device while it's landed. It won't be powering it at all while it's in flight, it'll be a little bit simpler for us to create. Also, it's not necessary for what we are expecting. And so then ideally then in the spring, we'll be able to test those batteries, purchase the batteries and test them along with the solar panels to see how much charge we can get in a certain amount of time, as well as test the batteries in low temperatures, because that's going to be a big test for us due to the construction of a battery and how it operates and how they react to below zero temperatures. So this is kind of an idea of the rest of the fall. And then for a budget, that's a really specific number for the batteries. It was calculated off a battery that was suggested to us. And after doing some more research, I found that that's probably not the right battery to use. So this budget is probably going to be sufficient for what we need. It's just going to be a different battery than what we originally budgeted for. And then the other thing we budgeted for right now is solar panels. Obviously, that's kind of that's an estimate, because we don't know how many solar panels or what kind of solar panels we need really until we can get the calculations and the math done of the actual structure.
So with Eagle Eye, we will be able to explore farther into the solar system, safer and more effectively. If disaster was to strike, Eagle Eye would be able to be there for the astronauts to take an up close look at the damage or the problem before they do an EVA. I've currently talked with some people that are in the Air Force Research Division, and they said that NASA is currently looking for a micrometeoroid device that could study those impacts more greatly. So this project could be used for that on the International Space Station, Orion, or any other craft that they are sending into the out of the atmosphere. SpaceX also seemed interested when I talked to them, because they're always wanting leading edge technology, and they wanted to be a part of something that they could possibly use when they colonize Mars or something like that, before they send their spaceship back up through the atmosphere, make sure there's no fractures or anything. That way it's safe and that the astronauts are not in any danger. I'd like to close it out with thanking our advisors, Professor Randai and Clayton Anderson, and the M2I department. Any questions?